and I will start the live stream right now.
All right, you can't see my face on the live on the.
I'm not sure. I think maybe those screens. So if you now commute, you can't see that window on the. Yeah, we can see you. You're actually on the top right, so it's fine.
Oh, okay, this is perfect. I don't see myself, but you see me.
We can see you. So you don't see yourself, but we can see you. So that's perfect.
Okay, perfect.
All right,
cool.
So let me do a short intro. Hi everyone. We are very excited to have Hugo here. Hugo has just returned from the vacation, and he is now very willing to tell you more about his research during the past year. He had been part of the Unikraft community for some time, and now he's a PhD student in University of Manchester. And he had been working on OS isolation, and based on his experience and skills with Unikraft, that was the basis for his research, resulting in scientific conference submissions and let's say a tool that's called FlexOS, that's currently under extensive development and research. That being said, I'm going to let him take the floor and give you a nice introduction into isolation and the way FlexOS and Unikraft work on this front. Hugo, it's up to you.
Cool. So hi everyone, I'm going to present FlexOS, a research project closely related to Unikraft that I have been conducting for about a year. It is about isolation, and it is mainly a cooperation between the University of Manchester, UPB and NEC. So I will try and give you an overview of the idea and its motivation, how we based it on Unikraft, along with some first numbers. Please feel free to interrupt me at any point in the presentation if you have questions, if I can clarify something. So if we take a look at current OS designs, it's quite clear that security or isolation strategies are typically fixed at design time. If we take the example of a typical monolithic operating system, such as Linux, there is the user kernel separation, the process abstraction, using the page table, and this is quite set in stone. We can make similar observations for other OS designs, such as microkernels or single address space operating systems. And the result of this is a view of the operating system that does not fit very well with modern specialization or hardware heterogeneity trends. Let me ask you a few questions. For example, what if you want to remove the user kernel separation in Linux? This is going to be to require a major rewrite, and this is going to be very expensive to maintain. What if you want to use cherry capabilities instead of the page table? This too is going to be a major redesign, and the same goes for memory protection keys. In the case of Unikraft, what if you want to isolate a library from another? There are plenty of use cases for this, actually. In this work, the main idea is to take a different approach and decouple security or isolation decisions from the OS design. What we want to do is to achieve a range of trade-offs instead of a single point in the design space. We want to achieve support for a range of isolation mechanisms, software and hardware, and granularities. In essence, what we want to do really is to specialize the operating system not only for performance, as we are doing in Unikraft, but also for security for given use cases. So you might think this is all very interesting, this is all very nice, but how is this related to Unikraft? And well, it happens that Unikraft is an excellent basis for flexible isolation. And so in order to achieve these goals, we propose a design based on Unikraft's highly modular libOS approach. And as you already know, in Unikraft, all kernel and userland components are developed as standalone libraries. And what we do in FlexOS is, as part of a porting phase, we pre-compartmentalize them. And with pre-compartmentalizing them, I mean we are going to identify cross-library calls and share data and we are going to replace them by an abstract construct. And by abstract construct, I mean gates and data sharing primitives, and these we define them as part of the FlexOS API. Then, at build time, these placeholders are going to be instantiated with a particular mechanism by the toolchain. This mechanism can be as simple as function calls if you want to put two components in the same compartment. But it can also be, for example, Intel MPK if you want to put two components in different compartments. Intel MPK is an ISA extension that is able to provide lightweight intra-address space isolation. You could also even put them in different VMs and let them communicate using remote procedure calls. In this case, it would be a bit extreme, it would be closer to microkernel, but it is also a valid use case. I know you might already have guessed the toolchain I'm talking about is Craft. So until now, I was pretty high level, pretty abstract. Let me go a little bit more into the details, and the best way to do this, I guess, is to present the compartmentalization API with a concrete example. So in this example, we're going to consider a simple call to receive from the application implemented by the network stack. Here, this call to receive is a cross-library call because the application is calling receive, which is implemented by the network stack. As part of the porting process, we would annotate shared data, and if I don't click, it's not good. We will annotate shared data and add gate placeholders. So this is all abstract. And at build time, if the network stack and the application are put in two different compartments, isolated using MPK, then we would replace these shared data annotations on the stack with a shared heap allocation, for example, and we would replace the gate placeholders with MPK gates. Of course, this would be quite different if we put the application and the network stack in the same compartment. In this case, we would not have cross-compartment shared data, and so we could keep it on the stack, and we would replace the gate placeholders with simple function calls. What we would obtain is exactly what we had before porting. In the current prototype, we use Coccinelle to perform these source-to-source transformations. Now, all of this is still a little bit abstract, so let's make it a little bit more concrete. In order to support flexible isolation, we essentially extended Craft to perform this instantiation step that I just mentioned. And so Craft.yaml now specify the isolation profile of the image. So the first thing that we are doing is we enable core FlexOS libraries. We also add a new compartment section that is going to declare compartments that will be present in the image. Here we have two compartments. The first one is the default compartment, and we use Intel MPK to provide isolation. The libraries section of Craft.yaml now also tells which compartment should be, in what compartment a given library should be put in. If this is not specified, then a library is put in the default compartment, and otherwise, for example, in the case of LWIP in compartment 2. So here, in this scenario, we isolate LWIP from the rest of the system using MPK. Now, this approach allows for a pretty large design space. And as you can think, not all of these configurations make sense, it being from a security perspective or a performance perspective. Also, if we take a look at the security side of things, pretty interesting questions arise. For example, how can we guarantee that the properties of components hold? Clearly, if we just blindly compartmentalize, a lot of mistakes can be done. For example, if you put plain C network stack together with formally verified scheduler, you're going to lose the properties of your scheduler. So another thing that we do on top of Unikraft in FlexOS is enrich the operating system with a tool that is able to, on the one hand, select configurations so that properties hold, and on the other one, further prune based on security and performance. I will not focus a lot of this. I will not focus a lot on this in this presentation, but I have backup slides. So if you're interested, we can go back to it during the Q&A. We have developed a prototype on top of Unikraft v05, which is essentially a private temporary fork. It will be released soon in the future when we published the full paper version. Personally, I would also love to have at least some of these merged into the Unikraft staging branch, and this is something that we'll work on in the future, I guess. We have developed gate implementations for Intel MPK and NVMs. We have also ported the network stack, the scheduler, UK time, and the file system to run as isolated components. We have application support for iPerf, SQLite, Redis, and Nginx. In this talk, I am going to present some results that we obtained with MPK and Redis, but there is more in the paper, and we're going to release more in the near future. So in this example, we have 4 different compartment configurations and up to 3 compartments. We gather results for 3 different payload sizes and 2 different gate implementations. One that shares the call stack and one that isolates it. In the implementation that isolates the call stack, we have 1 call stack per thread per compartment. So if we take a look at the results for the second scenario, we confirm an expectation that we had. The number of compartments impacts performance. But if we take a look at the remaining results, some more interesting observations can be made. Sometimes, because of communication patterns, reducing or increasing the number of compartments doesn't impact performance. And it is because the number of domain crossings doesn't change. We also observe interesting batching effects. Here, for 500 bytes payload, the cost of isolation is pretty much hidden. And so this highlights that sometimes the choice of isolation strategy that you want to make depends on the use case. And this is a very good point for specialization. Finally, the type of gate impacts performance as well. And this is another expectation that we had. So in all, this prototype and these few results highlight the design space that FlexOS can achieve, its complexity, and motivates for automatic exploration. As a conclusion, we highlighted the need for more isolation flexibility, whether it is for specialization purposes, to adapt to new hardware, or simply because the primitives that you are using broke. Current approaches take one isolation approach at design time, effectively representing a single point in the design space. In this talk, I presented FlexOS, an OS that decouples isolation from the OS design, making isolation decisions at build time. Unikraft is an excellent basis for flexible isolation for FlexOS, and more generally for research explorations on security. Now, this was a pretty short talk, but I have a live demo, so I would love to show you 2 different instances of FlexOS running, instances that I actually presented here. All right, this one, the one where we put the application and the network stack in different compartments, and the one where we merge them in the single compartment. It might take a couple of minutes, so while I'm doing it, if you have any sort of questions, I'm happy to try and answer it. I hope that you can hear me, that I was not talking alone.
Yeah.
In the room. Okay, great.
From what I've gathered, this is not necessarily applicable to like a multi-purpose general operating system.
Yeah, no. So yeah, maybe I can answer this question first. So it really remains in the spirit of Unikraft. So specialization towards a single application. And so we still have a single application. The idea is more to break this unikernel monolith into different compartments and to be able to do this in a very flexible manner. So to be able to first freely define the granularity at which you want to break this monolith. Either, putting each library in its own compartment, or putting a couple of libraries in one compartment and another one in a different one. That's the idea of freedom in granularity. And you also have freedom in technology. So being able to do this using Intel MPK, using different VMs, using Cherry, using SGX, whatever technology you can think of. Does that answer the question?
Yeah, I was just wondering. Yeah, and I was wondering if the same concept would be applicable to exokernels.
Yeah. Well, I would
a whole
say
different kind of worms.
I would say that I think that in some way you could do it. Yeah. I think that Unikraft is a really good basis to. You could probably implement FlexOS on top of quite a few OSs, especially component-based OSs or libOSs. They're all really interesting for this because they already have this very modular structure. That's what makes them interesting to base FlexOS on. So in this sense, FlexOS is not really tied to Unikraft. But Unikraft is a really good basis for FlexOS because it already has all these nice micro libraries that have very well-defined interfaces, and it has good application support. But yeah, you're right. We could actually do this on top of different libOSs or component-based OSs.
Thanks.
Cool. Right, while more questions come, I will do the live demo. So I have two windows. I'm going to use one to build my FlexOS images and the other one to do the benchmark. So here I'm essentially going to build it. I truly hope that everything will work as expected. So what it is going to do first is, since I did the make proper clean, it's going to re-download the libraries, but that's not FlexOS specific. This is Unikraft stuff. For some reason, it's taking time. Once this is done, it is going to proceed to the rewriting of the code. So it's going to do the transformations that I mentioned previously. What it's doing now is it's retrieving the list of files, the different libraries, and now it's rewriting them. As you can see, it's a research prototype. It's not optimized for compilation speed, but at least you see what's happening. And once it's done with the rewriting, it's going to build. It pretty much works exactly the same as a Unikraft image. Of course, if you are using VM EPT as a backend, so the case where you have different VMs, so you're not using MPK to isolate compartments, but different VMs, then you will obtain multiple images that we will have to launch separately. Here I'm only giving an example with MPK. Now it's building. By the way, the example that I'm building is ready. So. Shouldn't take much more time. All right, now I have a little script to start it. As you can see, everything is working perfectly. I'm going to illustrate that it works. You can already see some numbers. So that was for the scenario where we put whip in a different compartment. So now I'm going to give you another example where we put the network stack in the same compartment as the rest. I'm just going to clean up my build environment. This too is not very optimized for compilation speed. It's just going to essentially clean up all the code because we're doing source-to-source rewriting. So we don't want to have some stale rewriting somewhere. So I'm cleaning up everything. I'm going to rebuild and run it. And the nice thing is you will see the difference in performance, illustrating that we have a different isolation profile. While this is building, another question? Anything that I can clarify or anything that you'd like to discuss? No.
If you don't use compartmentalization, like everything is in one container, is it the same performance as you would have native?
Yep. So this is something that is quite nice. You only pay for what you get. So if you decide to put everything in the same compartment, you get the same performance as Unikraft. The reason is that we are doing these.
Yeah, if it just doesn't do anything, use the same code.
So yeah, what it's doing essentially is, So we're doing these rewritings. So if you put everything in the same compartment, the rewritings are going to produce code that is strictly equivalent to what you had before porting. So it will be the same as Unikraft. Does that make sense?
Yeah, it makes sense.
Cool.
Makes sense. I was just wondering, well, is there ever an instance where you would need to restructure your application to be able to compartmentalize it?
So in the current form of FlexOS, you do need some porting. However, it is not restructuring. It will be mostly a case of finding the data that you want to share, meaning if your application, like in this example, calls a function from another compartment with a buffer that is located in the application, then you need to annotate it. The instantiation of gate placeholders can be done automatically, but the shared data, it has to be done manually still. This is some interesting future work that I'd like to work on.
Right.
Right, so now I'm going to rebuild it. So yeah, clearly if we want to go for something that could be merged at some point into Unikraft staging, we would need something that has very little porting cost for kernel primitives and none for application code, which is not the current case. So for me, future work are clearly investigating automatic porting, investigating automatic detection of shared data. That's really something to explore.
Does this like create? Can there ever be an instance where like different compartments run in different threads and that causes race conditions?
So you mean, for
I'm not
example,
sure if that makes sense, but
so threads are essentially an orthogonal concept to compartments. You can have a thread navigating different compartments, in the call stack. Like you would have, if you take the MPK case, and you have an application thread calling a function in the file system, then the thread is the same thread that is going to execute the function in the other compartment. So it's if there is a race condition, it was already there before.
But if we are in the case where we have different VMs, then that would be different threads. And can one compartment be used by multiple parties?
Yes, so this is a difficulty, of course, that you start to get when you use different VMs. However, without entering too much in the details, if you I guess if you use appropriate synchronization primitives, you won't get this problem. But yeah, it's a complexity. I agree.
Yeah, I was just wondering if they both depend, if like two VMs depend on the third compartment that is run in a different thread, and it has some internal state that is not annotated as shared because it's library internal and it's not part of the interface. And then we have two different applications calling library code that is like a shared internal state. That sounds like it could break something.
Yeah, this is something we actually did think of this, but my intuition is to keep the same semantics as function calls, then you might not have problems. But I have to say I need to think more about it.
Yeah.
It's something that we are aware
pure
of.
functions, but not. Yeah, probably works with pure functions, but maybe not with function with side effects. Maybe.
Yeah, no, I agree, because it's the same issue that the people who did Sawmill had. They also had this issue, and more generally, when you have this problem when you try to decompose a monolithic kernel into a microkernel. No, it's a good point. I
guess
it needs more
opportunity to do research then.
Sorry?
A good opportunity to do more research then.
Yeah, I agree. I think it's an interesting point. But the VMEPT backend is not my own backend. It was done by Stefan. I don't know if he's here, and is currently being reworked by a KIT student. It's ongoing work. So interesting questions to answer. So yeah, as you can see, I just run
KIT.
I just run the
Might know.
Sorry.
I was just mentioning that I'm from KIT as well.
Cool.
But please continue on now. We've taken up enough.
Yeah. So no, I just wanted to mention that I just run the other configuration where we put LWIP together with the rest, and yeah, as you can see, we get different performance. So a small illustration. And now I'd say I'm done with the live demo, and I'm happy to continue the discussion.
Thank you so much, Hugo, for this. Any other, and thank you for the discussion as well and for pointing it out. I mean, having a demo is very interesting, getting to see how things are really working, and I think that you made a very good point of kind of this, what you're looking to pay. So if you're not going, if you don't want to pay anything with respect to performance, you'd only have one compartment. Where if you want to compromise on performance but build on security, you'd have this option of configuring where everything goes. Right. So any other questions or insights for Hugo? So this is kind of very interesting work. It's likely going to get published, and you guys are going to see more. Once that is done, maybe some part of it is going to be upstream, and you can also toy around with it.
Yeah, so let's say this is really ongoing work, ongoing research. So not everything is done, not everything is production ready, but I guess a lot of really interesting questions to explore.
Alrighty, so then that